I'm pleased to introduce our speaker, Mark Panning. I first met Mark a long time ago when we were both graduate students, and we got assigned to share a room at an IRIS meeting in the Grand Teton National Park. But we actually both overlapped as undergraduate students at Indiana University, where Mark got his BS in geological sciences. Mark then did his PhD in geophysics. He worked with Barbara Romanowitz at Berkeley, and then he did postdocs at Berkeley and then Princeton. After his postdocs, he did a professorship at the University of Florida until 2017, where he next moved to the Jet Propulsion Laboratory as a research scientist. So he's currently project scientist and co-investigator on the InSight mission to Mars, and he's also a co-investigator on the Dragonfly mission to Titan that's currently in development. But today he's going to talk about planetary seismology, 1 Mars year of InSight, and prospects for Titan and beyond. So thank you, Mark, for joining us, and I'll turn it over to you.
Thanks, Mike. It's great to be here virtually anyway, and let me see if I can successfully share screen. Always the first step of these things. Okay, so hit the button. How are we doing? Can people see that? I will make it into a presentation mode. Is everybody seeing that fine? Not hearing anything? I'm assuming it's okay. Once again, thanks for inviting me. I love to talk about this stuff. I started out doing seismology on Earth and talking about things like the deep mantle and stuff like that at that IRIS meeting. And these days I am 100% thinking about seismology on other planets instead, which is a lot of fun. But the first thing you'll learn when you start doing planetary seismology is it takes a lot of people to get anything done. These are big teams, and so I'm listing an author list here. So I have an author list here for just the Mars portion, which I'm starting out with. And these are just people that directly contributed figures and things to what I'm showing here. So it takes a big team to do this. But I could also show the full science team. And I'm not going to make you read all of those names, but it takes a lot of people to put these things together. And so everybody here is contributed to the science we're trying to do on Mars on a regular basis. But just to introduce you to what we're trying to do on the InSight mission and with planetary seismology, and so Mars is basically the third planetary interior to be investigated in detail, and I want to say straight out that I call everything that pulls itself into a sphere a planet. So our moon is a planet. Europa is a planet, and I will fight the International Astronomical Union to the death about this. I know they say we only have 8 planets, but I think that's an arbitrary definition. Okay, that's rants aside. So basically, what I'm talking about here is we're trying to do very basic seismology on Mars. The stuff that was done in the dawn of the 20th century for Earth. So how thick is the crust? What's the mantle look like? What's the size and density of the core? Where does seismicity happen? And these are the kind of things we're trying to get at on Mars for the first time. That was basically settled in the early part of the 20th century on Earth, and then 50 years ago or so, we started doing the same thing on the moon with the Apollo data that was put in place through the 70s, and actually had seismometers that kept operating until 1977. They actually turned them off about a month after I was born. So my whole life I've been waiting for new planetary seismic data. I didn't know it at the time, but this has been what I've been waiting for. And so now, we're getting this data back from Mars as well, and we're trying to get at what are doing comparative planetology and thinking about how these planets have evolved differently. So how are we doing it with InSight? So the the plan, and I'll have to talk in more detail about what's happening with one part of the plan. But so our primary science instruments were three science experiments, and the one I'm going to talk about the most, and the one I'm most interested in, is the SEIS, which is actually two different 3-component seismometers sitting here under a wind and thermal shield. But we're also doing radio science with these X-band antennas, X-band medium gain antennas on the side, and we use those to do radio science, which gives us some very detailed things about the rotation axis and the precession of Mars. And then we have this the heat flow and physical properties package, which was supposed to have a mole go down 3 to 5 meters and measure heat flow. We'll get back to that. We have recently gotten to the point where we have realized that it will not reach depth, but it's been a fun engineering challenge to try to get it down. But now we actually have a very good thermal properties probe that's sitting about 45 centimeters deep. So that's where we're at on that. But we also have a lot of other sensors that we can do science with, that are there to support the main sensors. We have cameras on the deployment arm. We have another camera under the deck that's always taking a picture of where the instruments are out on the surface. Of course, we have the deployment arm itself, which was used to put the instruments out on the surface, but we can do things with it like scrape and move dirt. We have a very good meteorological system. It turns out seismometers are really sensitive instruments, so they're really good at measuring lots of things. We can measure wind, we can measure pressure variations, we can measure magnetic variations. So all of these things have to be measured independently so that we know we're looking at ground motion. So we have pressure sensor, wind sensor, magnetometer, all on there as well. We landed here in this flat area called Elysium Planitia, which is near the equator of Mars, in between the rugged, high southern hemisphere of Mars and the low, smoother northern hemisphere of Mars. We're near that border between them, but this area right here, Elysium Planitia, is, in the words of our landing site expert, smooth, flat, and boring. We needed to be near the equator in order to get the energy we needed, because we're a solar-powered mission that was planning on going year-round. So we needed to be near the equator to reliably get energy year-round. And we needed to be someplace that was smooth, flat, and boring for safety. And so this is where we ended up, is here between the southern hemisphere and Elysium Mons, one of the larger volcanoes on Mars. This is a high-rise image of the landing area, so an orbital camera that's floating around Mars. We're in this area, and all these little yellow things that you can't read are all things that the geologists on the team named. They love to look at every rock and give it a name. But that's what our landing site area looks like. There's lots of these little craters here, which are called coronitos. These are secondary craters from a big crater that happened nearby. This was one of the first images we actually took of InSight itself. I think it's amazing that we have spacecraft going around another planet taking pictures of other spacecraft on that planet. So this was taken with the high-rise camera on the Mars Reconnaissance Orbiter. And here, this little Mickey Mouse looking thing right here is us. The middle part is the lander deck, and then there's the two solar panels off to either side, and then the saturated pixel right there is SEIS deployed on the surface before we put the wind and thermal shield on. It has a thermal blanket over it that's very reflective, and so it saturates that pixel. But you can actually see SEIS is deployed on the surface in that picture. So going into the science that we're doing in the mission, I'm going to focus on the seismology, but I wanted to talk a little bit about the radio science as well. So we're doing very precise radio tracking with the RISE experiment, and I've already forgotten what that stands for. Radio internal structure experiment. I don't know. There's too many acronyms in my life. I don't remember all of them. But basically, what it's measuring is how the spin axis direction is changing. So we can compare it with Viking data, and so we can look at how the spin axis is precessing through time, which that precession rate actually links into the state of the core. And then we're also looking at these little extra wobbles around that large scale precession, which are called nutations. And these are wobbles that happen actually multiple times per Mars year. We're seeing nutations that are either twice annual or 3 times annual nutations. And these wobbles are actually very closely linked to how big the core is and what the state is. The way I think about why we can look at these little wobbles and figure out the core structure is analogous to when you shake a jug of milk, and by looking at the wobble that happens, how much wobble you get when you shake that jug of milk, that tells you how much liquid's in there. This is the same basic understanding that goes into when you look at the amplitude of these nutations, that tells you what the state and state and size of the core is. So it's actually amazing to me, so basically we're just sending these radio signals here, and we listen for, early on in the mission, we listened for an hour at a time. Now we're listening for about half an hour at a time because our energy is tighter, because our solar panels are more covered in dust. But it lets us determine our location extremely well. So we know our location in inertial space within 10 centimeters. And the precession estimate we've done confirms that there is indeed a liquid core to Mars, at least an outer core. We can't determine whether there's an inner core or not. We're still getting the nutation data, but by looking at these nutations and looking at the amplitude, we've already constrained that the core radius has to be 1,800 kilometers or greater. Which is right up at the upper end of what our pre-mission expectations were. We also have a magnetometer on, and it's recording all the time. There's work to be done to look at the variations of that, to do electromagnetic sounding of the interior. But one of the interesting things is that the constant field, which represents the crustal magnetization, is about an order of magnitude stronger than what could be measured from orbit. Which gives us extra information on what scale length the crustal magnetization is varying, because basically as the scale length gets smaller, it gets harder to see from orbit. So this tells you that there are significant variations of crustal field at wavelengths less than 150 kilometers to keep us from seeing it from orbit, but to be so strong at the surface. Like I said, we have meteorology, and it's shown lots of interesting things. Mars turns to be very predictable day to day. The weather is pretty much the same day to day, although it varies over the course of the seasons. There's lots of interesting waves that can be seen in the pressure data. The pressure data has also shown us one of the interesting things is all these dust devils that go by, little low pressure vortices that go by. They're very prominent in the pressure data. We can actually also see them in the seismic data. But the interesting thing about this whole process is what goes into trying to put a seismometer on Mars. So Mars does not have plate tectonics. And so we knew that the seismicity was going to be significantly less than Earth. We knew that going in. We had estimations that the seismicity was going to be somewhere between what it is on Earth and what it is on the Moon, where there's obviously no plate tectonics, and it's very dead. There's not even any volcanism. There's still some remnant sort of volcanism going on Mars. So we expected it to be more than the Moon and less than Earth. And through a variety of arguments, we came up with specific numbers, but those were the main constraints. And so we needed to make sure we had a really sensitive seismometer to catch the few Mars quakes we were going to be able to see. And so the target for the very broadband seismometer, the VBB seismometer, was accelerations measured and a few times 10 to the minus 9 meters per second squared. And once you convert that to displacement, we're looking at amplitudes of displacement that are smaller than a hydrogen atom. And so, this was our design sensitivity. Actually, we exceeded design sensitivity. We had a lot of, safety margins on all of our performance estimates, and VBB did not need any of those safety margins. We're getting the performance we want. We're regularly getting noise floors and measured of, and a few times 10 to the minus 10th meters per second squared. So that's more like this dot right here is what the precision of our measurement. But in order for that to be useful, you have to deal with all the other noise sources. So we have to understand all of these things. And so that's why we have all of these other instruments on board. So here's one of our first selfies taken after landing, when the seismometer is still sitting here on deck, and this is the wind and thermal shield that will eventually be put on top. It's actually covering up the pressure inlet right now. And so this was, almost on the surface. It's actually very comparable to as close as a seismometer ever got to the surface of Mars before. The Viking landers both had seismometers on their lander decks, but they were never deployed onto the surface. They stayed on the deck. Viking 1 shown here, I think Viking, I always get them confused, I can't remember, but I think Viking 1 was the seismometer that didn't never uncage properly, so it never recorded anything. Viking 2 did record data, but it was mainly measuring how much the lander deck rocked in the wind. So we were really wanting to get deployed on the surface with InSight. And so that was the challenge we faced. So on the right, I've got a movie from our instrument context camera showing the whole process of getting SEIS deployed onto the surface. And so this picture on the right is actually the first picture we took upon landing. It's still got the lens cover on and it's covered with dirt. And we're thinking, okay, we're going to remove the lens cover and all that dirt's going to come off. It turns out the seal wasn't perfectly well. So when the lens cover comes off here in a moment, you can see we're still covered in dirt. Eventually that all fell off, so that's okay. But so it took us 22 sols to get it out on the surface. And then there was lots of adjustment of leveling and lowering and all of this. And then we released the tether so it fell down to the surface. There's this thing called a load shunt assembly, which is a little loop to try to decouple us from tether motions. And then we had to pull the tether back to open up that load shunt assembly, which took us a long time trying to get the scoop to pull that tether back. We finally did it there about sol 60. And we did a lot of imaging to make sure we'd opened it correctly and everything was happy. And then the wind and thermal shield flies in there around sol 66. And then there's lots of imaging and adjusting, making sure we're happy and that the skirt's coming down to shield us from everything. And so sol 70, we finally released. So 2.5 months almost to get one seismometer deployed on the surface. So for anybody in this group who has done field seismology, just be happy. It usually doesn't take you 2.5 months to deploy a seismometer. It's a much slower process when you have a robot that you can command once a day or so, and then you have to wait another day to see how well you did, so that the day after that you can begin to plan the next step. It's just a very slow process when you're always dealing with these sorts of delays on how often you can command and how often you get the data back. So here on the left here is this thing I was calling the load shunt assembly. This is basically a little loop in the tether that we pull open so that the motions of the tether on the ground don't get directly coupled into the seismometer. It's more or less when you do an installation of a seismometer and a volt, you put a loop of cable around it to try to decouple it from cable motion. This is the same concept. So one of the questions that always gets asked when we were planning this mission is, what are you going to do with a single station? Because everybody took intro seismology or something like that where they learned you need 3 stations to locate an event. And the short answer is no, you don't need 3 stations to locate an event, but you do need good data. So you could, if you have your PNS waves, you can look at the separation between S and P times and use that to get your distance. If you have a rough knowledge of the velocity structure. And then if you look at the polarization of the P wave coming in and the S wave coming in, you can look at those and determine the direction that the earthquake or Marsquake in this case came from. And so if you know the distance and the direction it came from, you have a location. So what does the seismic data look like on Mars? It's very predictable day to day how it varies. So what I'm plotting in this figure is basically each row of this figure is a spectrogram of data from InSight, from the VBB instrument. And the yellowish colors are high noise time periods, and the purplish colors are low noise time periods. And each day here is one sol on Mars, which is about 39 minutes longer than a day on Earth. The two lines on here are sunrise and sunset times over the course of the Mars year. The top row here is Sol 72, when we finally got all fully operational. And the bottom row here is yesterday. And this dashed line right here is one Mars year from Sol 72. What's interesting is that it's almost always noisy during the day. There are some parts of the year where it's a little quieter during the day, but it's generally very noisy during the day. And then about an hour before sunset, things start calming down. And during this portion of the Martian year, which was a large portion starting in a year basically on Earth, starting in summer of 2019, we had this really quiet time through the evening hours. And that's when we've seen most of our Mars quakes. It got nice and quiet, far quieter than any station ever on Earth. And then we got into the windy season, the dust storm season again, and then we didn't see anything for a long time. There are very few events that happened between about July of 2020 and the end of 2020. And at that point, it finally, it's just recently started getting quiet again as we're wrapping around to the conditions we had at the beginning of the mission. And so we're just starting to see Mars quakes again. We've seen just under 500 events that we think are likely of tectonic origin. Most of these are what we call high frequency events. They have most of their energy above 1 hertz. The ones that are more interesting to me are the low frequency events, and there's about 30 or so of those low frequency and broadband events. These look more like regular teleseismic events. I don't totally understand the high frequency events, but that's the basic pattern of data we've seen, and it takes clever eyes to see the data here. So what I'm showing here are spectrograms of individual days when we have events, and I dare you to see the events. Some of them they're fairly clear, but some of them it's hard to see. So basically we have high frequency on the left and low frequency on the right in each of these diagrams. And so, you know, I'll say right here, this is one of our biggest events right here, Sol 173. And that's the event right there, that little caterpillar looking thing right there that's happening towards the end of the day across the low frequency band. But you can see a few others here and there. I'll highlight them so you can see them, but these are subtle signals because they're little Mars quakes. Here's the first large event we saw is Sol 173. And when I say large, I'm being kind. It's a magnitude 3.7 event, so this is not a big boy, but it's one of the larger ones we've seen. And you can very clearly see the P&S waves coming in on here. Their polarizations are actually very nice, but you can also see one of our problems. This signal right here is a glitch. It's some thermal crack or pop somewhere either on the seismometer assembly or in the tether that's overlain on top of our data, and it happens right after, you know, about 20 seconds or so after the P wave, and it's really frustrating, but that's what Mars gives us. So, but you know, we can work around that. We can do deglitching and try to remove that. But these are signals that are always challenges on Mars. Even with that, we're able to start doing some, kind of good seismology on Mars. So, most of these things, the only clear arrivals are P and S waves. But we're working on finalizing a paper that's looking at multiple surface reflected phases. So you can see PP, PPP, SS, and SSS after several events. We have also published a little bit of work, and we're working on a final paper that's looking at crustal thickness from receiver functions. So for those of you who don't know what receiver functions are, I know some in this audience probably do. But basically, we look at around the P wave arrival and look for arrivals that come in just after the P wave arrival. And those are related to waves that are converted to S waves at interfaces below the station. And so that conversion to S means it travels a little bit slower through the crust. And so you get these late arrivals, and through our three best events, 183A, 173A, and 235B. And the names here represent the sol that we saw it on of the mission. And then there's the last letter is if there are multiple events on a single sol. So we can see that there's some consistency between the three different events where there's a lot of noise in there, but there's three clear arrivals. And it turns out you can interpret those as either two interfaces with the third bounce being an extra reflection within the top layer, or it could be three interfaces. And so this is telling us crustal thickness under our site. And so we're just now getting to those results. One of the interesting things that come out of those same three events is they're actually all located in a similar area. Well, in particular, the two best events, 173 and 235, are both located in this area called Cerberus Fossae. This is actually an area where we expected to see seismicity before we got there. It's some of the youngest volcanism on Mars. They're long fracture systems on Mars that have lava flows that have come out of them that are geologically young. That's all we can say for sure, but they have all happened in the last 10 million years, which is geologically a blink of an eye. Compared to like the vast majority of the surface of Mars that is billions of years old, this is saying something. And there are these long, very sharp-sided fractures that actually show rockfall trails where along an entire fracture system there are places where you see fresh rockfall trails along a relatively long stretch of the fracture system that were interpreted as rockfalls caused by single shaking events. So there was a place that we expected there might be Mars quakes, and sure enough, our best two events are located right there in that area. That was really interesting and something I was really excited about, because we're basically confirming tectonics in an area that the images had suggested there were tectonics. This is actually a paper that just got accepted yesterday by Minka Brinkman and others, primarily out of ETH Zurich. But looking at those three events, you can actually start doing waveform inversions for moment sensors. It's challenging and uncertain and difficult, but the best of the three events, 235B, if you look at it, it actually is very, this was a Bayesian inversion technique, and they got very consistent results that were looking at something that had an alignment that was very close to the mapped alignment of the fractures that looks like a near vertical normal fault, which is surprising. The 173 is less clear and looks to be more oblique, but is not inconsistent with that interpretation. And 183A is just generally much uglier. It's not as good at an event, but this is additional confirmation that this really looks to be tectonics in this relatively young volcanic area. We can also estimate seismic activity rate by the number of events we've seen. Our pre-mission expectation is this red line right here. The moon sitting down here. This is the actual moon observation. This is the range. If you take it up to the top, as if you scaled the size of the moon up to the size of Mars. And you could see our guess for seismicity was basically between lunar seismicity and intraplate activity in the US. And it looks like we're basically consistent with that expectation, with the notable exception that we haven't seen as many events above magnitude 4 as we would have expected to see. This could just be bad luck, but with the general tectonic rate we're seeing here, we were expecting to see a handful of events over magnitude 4, and we have yet to see any. So we either have a planet that's not generating large events, or we're unlucky. And at this point, we don't have a long enough record to say that for sure, outside of 95% confidence interval, but it's certainly an interesting observation. I should point out that our prime mission actually ended, and technically at the end of November, for various budgetary reasons, it was extended to the end of 2020, but we just got announced our extended mission that goes for another 2 years. So we are technically funded to continue operating on Mars until the end of 2022. The other instrument besides the seismic instrument is heat flow probe. It's basically a self-driving nail that was supposed to go 3 to 5 meters down and came out of this housing and traveled down. And basically it's trailing thermometers behind it, so you can measure the temperature gradient and therefore the heat flow. This was actually a cartoon that the Oatmeal put out at the time of our landing, because he likes the idea of the mole. But regardless, it was, that was the plan. It was supposed to hammer itself down and get down into the subsurface. And once we released it, it quickly got down to 35 centimeters and then did not go any farther. And we were not happy with that. And then, as a matter of fact, we started trying things to push against the side to let it go, and and to push down on the ground. And instead of going farther down, it backed itself out. So after a lot of work, it was gone from being 35 centimeters down to about 10 centimeters down, and that was frustrating. So then we did a lot of work to, I'm showing here our various, we basically started pushing on the top and hammering down while pushing on the top, and got it back in the ground, and then did a last set of pushing at it with an angle to get it totally buried. And then the plan was to put more dirt on top of it and see if it would start hammering on its own. Unfortunately, we did our final test with letting it do that about 2 weeks ago, and it did not make forward progress. So this is a picture that was just taken on the surface of Mars within the last few days. Looking down on the site, it's now totally buried. We've successfully totally buried a mole about a total of 40 to 50 centimeters down. But unfortunately, it will go no farther. We have accepted that that is the case. So unfortunately, space is hard, I guess, is the short answer there. So summarizing the insight portion of this talk, trying to do seismology on another planet is a long, slow process. It's, robotic deployment is not an easy process. I shouldn't go to reserve figures, but the data is actually quieter than anywhere on Earth. If you look at the frequency band around, say, 10 seconds, we're about 1 to 2 orders of magnitude quieter than the best installations on Earth. And that is, of course, not saying anything about the quality of installations on Earth. It's because in that frequency band on Earth, you always hear the oceans, no matter where you are. And so if there's one thing we've proven with InSight, is that there are no oceans on Mars. We do not see the microseismic noise on Mars. It's much quieter than that. So yeah, so that's takeaway for Mars. If you like any images, you want to look this up, you can go to mars.nasa.gov, InSight, and as soon as, basically images are available immediately. Science data you can get through the Planetary Data System or through IRIS Data Management Center. If you do want to work with InSight seismic data, feel free to contact me. It is a non-intuitive data set in a lot of ways because our sampling interval frequently changes for various operational reasons. We switch between engineering and scientific mode, and so understanding how to work with the data is not trivial, but I'm happy to work with anybody who wants to play with the data. I would love to see more Earth seismologists working with this data. So second part, I said I promised I'd talk about seismology on Mars and also what's in the future. And so the second part here is to look at seismology on Titan. And it turns out in the last round of what NASA calls its New Frontiers program, which are competed mission proposals that have a budget in the ballpark of $1 billion. They chose to fund this mission, which I'm a co-investigator on, called Dragonfly, which is going to Titan, a moon of Saturn. And basically, we're flying a drone on Titan. It turns out Titan is a great place to fly. It has an atmosphere that's has a pressure at the surface about 50% denser than Earth. So it has a very thick atmosphere, mostly nitrogen, but other organic stuff in there. And it has a gravity that's about the same as our moon. So much lower gravity than Earth and thicker atmosphere means, hey, let's fly. Ralph Lorenz told me once that if Icarus had tried to strap wings on and fly on Titan, he would have succeeded if he could survive the fact that it's 94 Kelvin and so therefore very cold. But you could fly very easily on this planet. So that's our plan. We land. And then every 2 Titan days, which is about once every Earth month, we can fly many kilometers, maybe tens of kilometers to a next site. So we can sample many places on Titan, but at each place we're actually going to be lowering a seismometer below our belly and recording seismic signals for about a month in one place. So how do we do seismology on Titan? Well, it turns out Titan is one of the things that we call icy ocean worlds. These are the moons in the outer solar system that have significant ice layers, ice and liquid water layers, most likely. And so this is kind of a bestiary of some of these icy moons that we may encounter. I got my start, the whole reason I got involved in planetary seismology is during my first postdoc at Berkeley, I was funded to basically make up seismology for Europa for part of a planned mission called Jupiter Icy Moons Orbiter that never happened. I would love to talk more about that mission because it's an interesting story. But Europa has remained an interest of mine, and it has basically a thin ice 1H, which is ice like we normally have over a very thick ocean, order 100 kilometer thick ocean. And then a rocky and metallic interior below that. And then some of these bigger moons of Jupiter, Ganymede and Callisto, likely have higher pressure ices below it. So ice 3, ice 5, ice 6. Ganymede may have what we call the Dagwood structure, where it's actually got sandwich structure of liquid water between high pressure ice layers. And Enceladus is a really interesting body that I think would be really fun to go to because we know it's geologically active. There are these active plumes coming out of its south pole area all the time and actually creates one of the rings of Saturn. You know, it also has ice and an ocean. Titan here is bigger, it's more in scale with Ganymede and Callisto. Likely, well, may or may not have this high pressure ice layer at the bottom. It turns out if it's cold enough to have a thick ice shell at the top, it likely has a high pressure ice layer at the bottom, but if it has a thinner ice shell, it's warm enough that it won't have high pressure ice. So these are interesting things that we want to look for. And so generally on these ocean worlds, all the figures I'm showing here are actually not from Titan. I'm going to places where we can see the surface better. Titan is covered in a thick atmosphere that has a haze, so we can't see its surface very well. But we can see the surface of places like Europa and Enceladus much better. They're covered in fractures. So there's things happening on there. And they're all very close to these gas giant planets. So they have big tides. There's probably fluid flow. There are active processes like plumes. There may be impacts, although that's pretty low probability to see. And by looking at seismic signals from all of these sources, we can look at things like how thick is the ice shell before you get to the liquid water? How deep does the ocean go before you hit the rocky interior? Are there high pressure ices? You know, what are these? These are a lot of questions we'd like to answer with seismology on these icy ocean worlds. And so where does this all, where do the signals come from on these planets? Well, we think probably a lot of it is going to be tidal cracking, ice quakes happening because of tidal cracking as these planets deform. This is once again Europa over here, but this is showing how it tidally deforms during each trip around Jupiter. It's always pointed towards Jupiter. It has the same side always pointed towards Jupiter, but it has a slightly elliptical orbit because it's in a resonance with Io and Ganymede. And because of that, it has slightly elliptical orbit, and so the bulge changes over the course of the cycle. And so there will be cracking associated with that, and then there's going to be ocean motions. And then on Titan, compared to Europa, which doesn't have an atmosphere, there are actually other sources we can think about. There can actually be something kind of like microseismic noise on Earth, because it actually has lakes on the surface, at least in the polar regions. They're just not water lakes. They're liquid ethane, methane lakes. And certainly there will be the effect of atmospheric noise. And I think that's almost certainly going to be the dominant noise source that we have to deal with on Titan. So a lot of what we're going to do, if we're looking at Titan, we're going to look at phases that reflect. This is from a paper back in 2003, which is one of the first ones to look at what kind of seismology you want to do. So you'd look at timing of reflections off of the ice-ocean interface and the ocean mantle. Excuse me, ocean mantle interface, and these are going to be in the kind of 1 to 10 hertz range. But there's also interesting stuff that happens at lower frequencies, and this is stuff that I've been working on a lot. And starting when I first started making up planetary seismology, there's a lot of interesting waves that get trapped in the ice shell. So what I'm plotting here is 3-component data, and these are spectrograms. So it's low frequency at the bottom, high frequency at the top, going from about 0.01 hertz up to about 2 hertz in this case, and then time on the x-axis, and it's about an hour's worth of data. In the high frequency band, you see body waves bouncing around. So these vertical lines in here, these are body waves bouncing in the ice shell. But in lower frequencies, you see some interesting waves. So there are surface waves like Rayleigh waves, and then there's this thing where you can see it's arriving later and later and later as you get to lower and lower frequencies. This is something called a flexural wave. This is the whole ice shell bending like a plate. And the pattern it makes, and this first arriving energy right here happens at a characteristic frequency that depends on the ice shell thickness. So it's an interesting thing. There's other trapped waves called things like Crary waves that get trapped there that are also very diagnostic of how thick the ice shell is. Oh, I don't know why that just went by. One thing that's interesting to do, and I hope you guys are going to be able to hear this, we may, based on our models of what seismology could look like on Europa, we made sonifications of that. And so here's a 5-kilometer thick ice shell sped up by a factor of 500 to put it into audible frequencies. So if you're listening, you can hear all these like downward sweeps. Pew, pew, pew. Those are those flexural waves. It gives you those kind of like laser noises. If you have a thicker ice shell, that dispersion happens more rapidly. So instead of having long drawn out relatively long drawn out sweeps, they happen more quickly. So you can hear the difference between the thicknesses of the ice shells that way. But likely this is going to be superimposed on the noise. Our model of ocean noise suggests it should be relatively low frequency. So it basically gives you a rumble sitting underneath those laser sounding sweeps. That's just, our ears are a different way of processing data. So I like to do that sort of thing. So, but basically that data came from trying to assume what kind of pattern of ice quakes we should see. And so in order to model what we're seeing on a place we've never been, I assume it's going to follow a statistical distribution similar to what we've seen on the Earth, the Moon, and Mars. And in other words, that it follows a Gutenberg-Richter relationship, where every time you get roughly 1 magnitude unit bigger, you get roughly an order of magnitude fewer events. And so that'll give you a pattern where you get tons of small events and a few larger events. And so these few larger events are our signal, and the more or less continuous smaller events are our noise. And so we can do this on Titan to figure out what kind of signals we're going to get. And we can compare that to various instruments. And the instrument that is something that's like the instrument we will be flying on Dragonfly is like this red line here. So that's the noise level of it. This background curve here is what we think the continuous cracking at low magnitudes is going to produce. That's the noise pattern you get. And then the biggest events pop up here. So the Dragonfly seismometer should see the largest events, but will likely not see the background ice cracking noise. And you know, this is order of 50 decibel above the instrument sensitivity. So that's a pretty big error margin for whether we'll see those events or not. And these are the size of the biggest events we expect to see in every 1 or 2 tidal cycles. So basically at each time we sit still, we'll see something that looks like these events, hopefully. So that's the story there. We also considered whether, this is work I did with Simon Stahler at ETH Zurich, with wondering whether we'd be able to see the equivalent of microseismic noise. The blue areas up here are these methane lakes. They call them seas on Titan, but you know, call them what you want. There's a few down in the south polar region and several up in the north polar region. Dragonfly is going to be landing near the equator. Basically, the colors here are saying when the microseismic noise from waves on these lakes would be visible. And the issue here is that wind on Titan is very weak. You know, generally a lot of weather gets driven by temperature gradients. And Titan has very little in the way of temperature gradients. It's far from the sun, and it has a hazy atmosphere. So the surface is more or less continuously at 94 Kelvin all the time, pretty much everywhere on Titan. And so there's not a lot to drive weather. So winds are quite weak, even though it has a very dense atmosphere. And so since the winds are low, you don't get big waves, and so you don't get big microseismic signals. So likely to see the microseismic signal, we'd have to be pretty close to the poles. And we are not going to see that with Dragonfly, most likely. But the big question is, what does atmospheric noise look like? And you'd think that maybe it would be nice to look at Earth, but it turns out atmospheric noise is not the driver of noise in most places on Earth. It likely is, well, we know it's the driver of noise on Mars, and it likely is also the driver of noise on Venus, which I'll get to how we can use that because there's not very much data from Venus. But we try to scale from Mars and Venus to figure out what the atmospheric noise is going to look like on Titan. And so the gray lines here are typical noise patterns on Earth, where you got these 2 peaks that are driven by waves on the ocean and their nonlinear interactions. The red, green, and blue lines here are noise on Mars from InSight. This was on deck. This was once we put ourselves on the ground, and this is when we covered ourselves up with the wind and thermal shield. Probably since we are lowering to the ground, the comparable one for Dragonfly is this green line maybe. But we have to scale it. And so basically we can scale by the atmospheric acoustic impedance. So how well does the atmosphere couple into the ground, which is much higher on Titan. But we also can account for the fact that there's a reduced solar flux. So that likely is much lower on Titan. So there's two different methods. We can also try to scale by dynamic pressure, which is atmospheric density times the wind speed squared. As I said, we have measured wind speeds on Mars, and we can model them on Titan. Either way we do it, if we scale up from the on-ground data on InSight, if we scale by the impedance or we scale by the dynamic pressure, we get something that's basically like near in the few second band where it will have, the noise will be similar to the quietest stations on Earth, approximately, and noisier than what we see on Mars. And the simulated peak signals are sitting up here. So once again, order 25 decibels or so above our estimated noise. We can also try to scale from Venus. This is interesting because Ralph Lorenz and I came up with an estimate of what the noise level is on Venus. And this was very challenging because our data from Venus is basically 10 or so minutes of geophone recordings, but not the actual geophone data, just a counter that said how often the geophone exceeded a certain level over that 10 to 15 minute time period on a couple Soviet Venera landers. That didn't last very long because Venus is a terrible, terrible place. But anyway, based on the count of how many times it exceeded that threshold, we estimated that that would actually be a similar level as normal Earth station. So we say up here, you know, like a noisy-ish Earth station should be is similar to the Venus noise. Very rough approximation. And then we can do the same sort of scaling using acoustic impedance and solar flux, and that predicts down here. So that actually is a quieter prediction than Mars. So we have a range of possible atmospheric noise. So this is the range of expectations that we have going in. So you sum all of this up. The microseism is likely down below our detection threshold. The atmospheric noise is either close to our detection threshold or 20 or so decibels above that. And our largest signals are 20 to 25 decibels above that. So short answer is the instrument won't see background tidal cracking, but probably will be constantly recording atmospheric noise, and hopefully we'll be recording once a month or a few times a month these larger ice cracking events. And so to kind of sum it all up, we do think these largest tidal cracking events are going to happen every few tidal cycles, above the instrument noise and above the atmospheric noise, using our best guesses right now. We may be proven wrong, but that's what we think. We don't think we need to worry about atmospheric microseismic noise, but atmospheric noise is going to be really important. And so, yeah, I'll stop there. I've got other figures I could show if people have questions, but I'll give you at least 6 minutes for questions here.